To investigate the graphs of sine and cosine functions, we're going to use a technique that we've used in the past. We're going to begin with kind of a degenerate form of both of those functions, look at their graphs, and then kind of add coefficients here or there to see how the behavior of the graph will change. And fundamentally, we're going to take a point plotting approach to graphing. Well, consider f of x equals sine x, and the working model, the model for graphing is y equals sine x, as we've seen in the past. Now, we can think of the x here as either a real number, or an angle measured in radians, or an angle measured in degrees, and we get the same result in all of this study. Using the point plotting method, we just fill in a table of values. Now, I've allowed x to take on values 0, pi over 2, pi, 3 pi over 2, and 2 pi. I'm thinking in terms of real numbers here, but if we wanted to, we could say 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees, and again, have the same result. Okay, so plugging in here, either using the calculator or studying this using the unit circle or using right triangles, we find that when x is 0, sine x, which is y, is 0. And when x is pi over 2, the sine of pi over 2 is 1. And when x is pi, the sine of pi is 0, and so on. Okay, let's plot the points. Now, in structuring the coordinate plane for graphing, we need an axis that well, the x-axis is an axis for either the real number or the angle measured in radians or the angle measured in degrees, you see. And so it really follows the same idea that we have had all along with graphing. Now, one cycle of the graph will occur in an interval that is 2 pi in length. And so I'm identifying the position of 2 pi here, and I'm identifying the position of 4 pi. And now we need some significant values in between these two. Now, right in between 2 pi is pi. Right in between 0 and pi is pi over 2. And in between pi and 2 pi is 1.5 pi, or 3 pi over 2. Now let's plot points. Now I'm just going to look over here and plot the points. And you just stay right here and watch how this graph is going to behave. 0 goes to 0. Pi over 2 goes to 1. And then at pi, the graph comes back to 0. And then at 3 pi over 2, the graph drops down to -1. And then at 2 pi, it comes back up to 0. And then the whole cycle starts over again. And the graph kind of looks like the graph of a polynomial function in that it's a continuous graph and it's just kind of curvy. It goes like this.
Leading up to January the 6th, post after post, the president's supporters confirmed.
You see, that's one complete cycle. Now that complete cycle for a graph of sine or cosine is called the period of the graph, and this distance above the x-axis or below is called the amplitude. And so the amplitude for this graph is 1. You see, and that distance is 1. This distance is 1. Okay, so amplitude and period. Now, the graph continues on forevermore in both directions here, because we're talking about all real numbers as replacements for x. Now, in some circumstances, we will want to limit the domain here of our functions, but for all practical purposes, we have to assume that we're going forevermore in both directions. So we go out this way, we go down to the bottom of the amplitude over here at a negative pi over 2, you see, and continue just the process this way. In the other direction, well, let's see, in between 2 pi and 4 pi would be 3 pi. But the idea is that if we have these little intervals, you see, of the important points for the graph, then we can just go from interval to interval and understand what's going on. That from here, we go to the top of the amplitude, you see, at the next important point. And then we come back to the x-axis for an x-intercept, and then to the bottom of the amplitude for the next point, and then back to an intercept. So the graph then goes like this. Now, in a similar way, we can analyze the graph of the cosine function. We just think f of x is cosine x, or y equals cosine x, and now we make a table of values. Now, the table begins the same way. We're utilizing these important points for x, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And now we fill in for y. And again, we can fill in a lot of different ways, but we find the cosine of 0 to be 1, the cosine of pi over 2 to be 0, the cosine of pi to be negative 1, the cosine of 3 pi over 2 to be 0, and then 1 once again. And these values for y look roughly familiar to the values for y on the sine curve. And in fact, the curves look pretty much the same, except they're just kind of shifted a little bit on the coordinate plane. Let's have a look. 0 goes to 1. So when x is 0, y is 1. And when x is pi over 2, y is 0. And when x is pi, we go to the bottom of the amplitude to negative 1. And then when x is 3 pi over 2, we go back to the intercept. And then when x is 2 pi, we go to the top of the amplitude. So for the cosine curve, we're starting at the top of the amplitude. We go through the x-axis. We go to the bottom of the amplitude, and then back through, and then to the top again. So this is the fundamental cosine curve. And then it obviously continues in both directions, just like the sine curve did. So from the top of the amplitude, we go back to an intercept, then the bottom of the amplitude, intercept, top of the amplitude. So here's how it looks. And here's how it looks over 2 periods. You see, we're graphing 2 periods of this function. Okay, let's talk about domain and range. We can kind of see it here, and we can kind of see it from our work in the past, that the domain, the acceptable replacements for x, would be all real numbers. We can take the sine and cosine of any real numbers that we choose. Now the range, because that amplitude, you see, was the highest point on the graph was 1 and the lowest point negative 1, the range is between negative 1 and 1. So here's the range of both of those functions. Now let's start to add a little interest to the graph. Let's just tack on a coefficient here. Consider y equals 3 times sine x. Now, to construct the graph of this equation, we'll kind of go from the graphs that we talked about before, the basic sine graph. And the way to do that using a point plotting method is like this. Make your table of values so that you have 3 columns in the table. An x column, a sine x column, and then it's pretty easy to calculate a column which is 3 sine x, which is y here, which is the y values here that we're calculating. So for the x sine x, you see that those are the columns that we've had before. When x takes on these values, sine x takes on these values. So 3 sine x means 3 times all of these rascals. So 3 times 0, 0, 3 times 1, 3, 3 times 0, 0, 3 times negative 1 is negative 3, 3 times 0, 0. Now, remember that y is 3 sine x, so this is y, and this is our xy pair then that we're plotting to see the graph. Okay, so away we go. Now, when in structuring the coordinate plane for graphing, we just make a vertical plane, and now I'm identifying 3 and negative 3, and we'll see why in just a minute. But on the horizontal axis, I'm thinking about 0 to 2 pi, 1 complete cycle, you see, and then just subdivide this little interval into 2 parts, and then subdivide that into a couple of parts. You see, just take half, and then half of those halves. And now this is pi and pi over 2. And very quickly, we can sketch the graph. This is 3 pi over 2. Okay, now we just plot a bunch of points. 0 goes to 0, and then pi over 2 goes to 3. Pi goes to 0. 3 pi over 2 goes to negative 3. And then 2 pi goes back to 0. And the cycle continues in both directions. So the graph then looks like this. And we're seeing that when we tack on a coefficient, that just as we may have suspected, come back over here with this, that y equals sine x has a particular kind of pattern, a particular behavior for the graph. Now, these are vertical distances associated with sine x. Right now we're talking about 3 times those vertical distances. You see, so no wonder the graph tends to stretch this way. For every vertical distance that we had in the sine curve, we are thinking about 3 times those vertical distances for the curve associated with this equation. So it turns out that when we have a coefficient, it will cause the graph to be either elongated or maybe squashed a little bit like this. You see, what if A were, instead of 3, 3 causes it to stretch this way, what if it were 1/2? So then 1/2 would be half as high as the original graph that we looked at earlier. And by the way, this is where 1 is on this particular graph. I have changed the interval distance for my vertical axis. So the graph here looks pretty much like the one that it did before, but notice that 1 is right here. So the graph of sine x for this coordinate plane would just go up to right here and then down to right there, you see? And so that it's really stretched up here to 3. But at any rate, it's the idea that that coefficient will cause a stretching or a compression of the graph. Now, if the a value is negative, think about what that would do. You see, if that a coefficient were negative, that means we would have the negative of some vertical distances that were associated with the regular sine curve. The negative of vertical distances, well, that's our concept from before of flipping the graph over. So if we were talking about an a value, and let me just talk about a pretty simple one. What about y equals the negative of sine x? You see, just the negative of sine x. Well, all that would do is take the regular sine curve, which is like this.
Oh, don't tell me somebody took it.
You see, that's the sine. Here's 1, and there's 1. So the amplitude here is just the 1. Okay, and it would just flip it over. So the graph of that rascal would be, well, think about flipping it over, and it would look like this. Now, I'm going to make it dotted here just for emphasis, but it would look something like that. So the a, that coefficient that appears here, the a that appeared over there, will tell us whether or not the graph is kind of flipped this way. If it's negative, it'll do this. And if it's positive, then it will stretch or compress. Now, it'll stretch if the number is larger than 1 or smaller than -1. It'll kind of appear stretched like this. It'll sort of look compressed if that number is between -1 and 1. And more generally, just to generalize the situation, for y equals a sine x or y equals a cosine x, the amplitude, it corresponds in a way with this a value. And in fact, the amplitude is exactly the absolute value of a. The absolute value is in here because the amplitude is really a distance, you see, from that horizontal midline of the graph, and that distances are always considered to be positive, and so that's why the absolute value is put onto it. Let's take a look at the situation on the graphing calculator. I've already entered y equals sine x, and I'd like to make a suggestion for you. In the window settings, I suggest that you change your x scale from 1 to something that gives us information about our intercepts and tops and bottoms of amplitudes, and that would be, for the sine curve, it would be pi over 2. So we can enter that as second and then pi divided by 2 like this. And as soon as we leave this screen, and if we were to come back to it, this would be in its decimal form. But enter it as pi over 2. And then when we graph, you see the graph comes up, and we can see that with that x scale at pi over 2, we can see the important positions or points on our graph. Here's pi over 2. Here's pi, which is 2 times pi over 2. This is 3 times pi over 2, 3 pi over 2, and this is 2 pi. All right, at any rate, here's one cycle of our graph, and then the cycle just continues forever. The graphing calculator is kind of neat in its ability to allow us to see that changes in the equation have certain changes in the graph. And here we can enter, for example, 3 sine x. And I'll close the parenthesis. Notice the parenthesis all automatically comes up on the TI-83. At any rate, here's the graph. And we see that the 3 is simply stretching the graph up and down. Our intercepts, though, are at the same spot that they were before. Let's try another little change. How about 1/2 sine x? That would be 0.5 sine x. And its graph. And as expected, the graph is just kind of scrunching down a little bit. It's sort of compressed against that x-axis just a bit. But again, the intercepts are in the same spot. Let's make another kind of change. Let's go back, and actually the graphs are getting a little convoluted here. I'd like to clear this one, and I will clear this other one. And I'd like to show you, actually I want to leave up 3 sine x. My bad. 3 sine x. I'd like to leave that one up. And I'd like to enter -2 sine x to show you what happens with that one and the graph. All right, here's sine x. Next will be 3 sine x. And the third one will be negative 2 sine x. And you see it just kind of flips the graph over. 2 sine x would be the flip over of this one. This little down part right here would be up if it were 2 sine x. So the negative sign just tends to flip it over. Let's look at something else. I'd like to look at the cosine curve with the sine curve. I'm going to take out these two graphs, and I'm going to enter cosine x. Now here's sine x. Here's cosine x. I think it's important for us to know that the significant points involved in the cosine curve are the same significant points as we had with the sine curve. 0 is the top of the amplitude for the cosine curve. Pi over 2 is an intercept. Pi is the bottom of the amplitude. 3 pi over 2 is an intercept, and 2 pi is the top of the amplitude. So the two graphs are actually identical, except one is shifted from the other. If we could somehow get either of these graphs to shift just a bit on the coordinate plane, they would overlay one another. We know that for the basic sine curve, one period of the graph, that is one cycle of the graph, occurs from x equals 0 to x equals 2 pi. Now, we want to make a change in the function a little bit and examine the resulting change in the graph. And the change that we're going to make has to do with a coefficient on x this time. Now, consider what we're taking the sine of if we have the sine of bx. You see, we're taking the sine of this value. We can think about it as a real number or as an angle, it doesn't matter. But it's the sine of this value, and it's that value that is going from 0 to 2 pi. That is, one period occurs from a bx value of 0 to a bx value of 2 pi. You see, because that's the angle that we're taking the sine of, or that is the real number that we're taking the sine of. It is bx that we're taking the sine of. All right, and it's that number that moves from 0 to 2 pi to give us that interval over which we have one complete period. Now, what does this lead to? Well, if we solve this for x, we find x to be 0, as we might expect. But over here, when we solve this for x, you see we have 2 pi over b. So our period is occurring from 0 to 2 pi over b for whatever value b takes on. Now, here's how it occurs in a problem. We have y equals sine 2x. Now, the period is from 0 to 2 pi over b, and this needs to be committed to memory. Or we can think about the discussion that led up to it to help remember it. But at any rate, we pop in the b value here, and that's the coefficient of x. And in this case, it's 2. And so we have 2 pi over 2. The 2's go out, and we have pi. So we're going to have one complete period from 0 to pi. Now, in constructing the graph, and I want to compare the graph of this function to the basic sine curve, which is given right here in the dotted curve. But we have a complete cycle from 0 to pi. So we have a complete cycle from here to pi. Now that means that all we need to do to structure the graph is identify those very important points that represent the top of the amplitude, the bottom of the amplitude, and the various intercepts. So we just need to take this interval and subdivide it by splitting it twice. We split it one time here, and this is the point pi over 2. And we split this interval and split that interval, and we have the important positions for the graph. We don't really have to identify the value for that point and the value for this point because we know the nature of the graph. And we know that the sine curve is just going to occur within that interval. So our basic sine curve starts at the bottom of the at the x-intercept, or we could say the bottom of the, no, it's not the bottom of the amplitude, it's at the intercept, and then we go to the top of the amplitude, and then we go back to 0, and the bottom of the amplitude, and then back to 0. So here is one complete cycle. You see, now I could continue the cycle, and I think I will continue it into one more period for this particular function, and it'll have another complete cycle in the next interval that is pi in length, which is right here. And so I'll take that interval and I'll subdivide it a couple of times. I have a division here. I want to divide these. And now from here to there, I go to the top of the amplitude, back to 0, bottom of the amplitude, back to 0. So now the graph just continues kind of like this. Okay, it appears then that when the value of b is a number larger than 1, it appears to sort of compress the graph this way. It causes the cycle to occur in a smaller interval. And it's also the case that if this is a common fraction, like 1/2 or 2/3 or something like that, it'll cause the cycle to occur over a longer interval. And we want to look at that situation in the next problem. By the way, this idea holds true with the cosine curve as well. In fact, let's take an example involving the cosine curve. We have y equals cosine 1/2 x. Now, in analyzing problems like this, you want to go through a thought process that also involves the amplitude. And here the amplitude is simply 1 because the understood coefficient here is 1. So I didn't write that in here, but in future problems we're going to want to write all of that information as we analyze the problem. Okay, so we have an amplitude of 1 and a period that is given by, well, let's see, the length of the period. The period, it starts at 0 and it goes for what length interval? That's really what we need to figure out. And the length of that interval is 2 pi over b. The b value in this case is 1/2, so it's 2 pi over 1/2, which is 4 pi. So we're getting a stretching of the graph in this case. Now, all we need to do, though, is create an interval that is this long, you see, and just go by the nature of the cosine curve to structure the graph. So that's what we're going to do. Now, I have drawn in here with a dotted curve, the regular cosine curve, the graph of the cosine function, but I need to stretch this out. So I need to double this interval out here, you see, and if this is 4 pi, then all of the cycle is going to occur within this interval. And so I need to take this interval and subdivide it twice. So I'll divide it in half. There's one very important point. Here's another. Here's another. Now, what's the basic structure or behavior of the cosine curve? And that's what's so important here. That's what we need to remember. And you'll be using these so often that there'll be no problem remembering it. But the cosine curve starts at the top of the amplitude, and then it goes to the intercept, and then the bottom of the amplitude, and so on. So we want to start the whole routine of graphing the function by starting at the top of the amplitude. And then at the next important point, which is here now, we go to the intercept point, and then at the next important point, we go to the bottom of the amplitude, and then back to the intercept, top of the amplitude. So it kind of looks like this. So we get a stretching of the graph like this. Notice the dotted horizontal lines at the top and bottom of the amplitude. This sometimes helps us keep track of the situation as we move along number lines that are stretched out a little bit this way, and it just helps to organize the information a little bit better. Consider now what happens if we add or subtract before we apply this operation called sine. And I want to say it that way because I want to relate it back to our previous discussions of transformations. Remember when we talked about transformations generally, we had a primary operation like squaring or square rooting or absolute value, something like that. And we said that we can understand shifts in the graph in terms of adding or subtracting before or after the prevailing operation. If we add or subtract after the prevailing operation, the graph simply moves up or down in the coordinate plane. We haven't seen that yet here. But if we add or subtract before the prevailing operation, then the graph shifts left or right in a direction we don't expect. Excuse me. Now, that's what's going to happen here, and that's called a phase shift. So it's just a shift of the graph left or right. Now we can see what's going to happen here by structuring a table of values. First we might think about amplitude. The amplitude here is the coefficient in this position, and it's understood to be 1. So the amplitude is 1. The period now is 2 pi over b. Now for this particular one, it's the coefficient of this, this parenthesis. You see, it's whatever number appears here that gives us the b value for this analysis of period, and that number is understood to be 1. So the period is going to be 2 pi. All right, all predictable situations. Now, the only unpredictable situation is this subtracting of 2 pi before we take the sine of whatever number we're talking about. So to analyze the situation, we might use x's that we've used before, and now evaluate x minus pi over 2. You see, 0 minus pi over 2 is minus pi over 2. Pi over 2 minus pi over 2, oh, that's 0. Pi minus pi over 2, oh, that's pi over 2. Then 3 pi over 2 minus pi over 2 is 2 pi over 2, which is pi. And then 2 pi minus pi over 2 is 3 pi over 2. Now, notice these values in here that look so familiar from our work before. These are the primary points that we used in the x column before. You see, they're just these values right up here. You see, and no wonder, because of this subtraction of pi over 2. Anyway, when we take the sine of these values, we get, well, let's see, for the sine of negative pi over 2, we have to be a little careful here, and it turns out to be negative 1. And then 0 goes to 0, and the sine of pi over 2, you see, I'm taking the sine of all the numbers that are in this column, because the numbers that are in this column are these guys, you see, that I'm taking the sine of. All right. So the sine of pi over 2 turns out to be 1, the sine of pi turns out to be 0, and the sine of 3 pi over 2 is negative 1. Okay, so let's go graph these points. Now, this is the xy pair that I'm graphing, okay, in all cases here. So I slide over here. This is the fundamental sine curve, and I want to compare it to the graph of the curve that we have before us, the function that we have before us. All right, 0 goes to negative 1. Here's 0, here's negative 1. Well, that's unusual. Pi over 2 goes to 0. Pi goes to 1. It's kind of predictable at this point, isn't it? I mean, we're going to go through the basic sine curve. It's just that we're starting at a different point. And then at 3 pi over 2, we go to 0. You see, back to the intercepts. And then at 2 pi, we go to negative 1, the bottom of the amplitude. You see, so the pattern of bottom of the amplitude, intercept, top of the amplitude, intercept, bottom of the amplitude, that kind of pattern holds forth here. Now, when we structure the graph, when we construct the graph, look at what has happened. You see, it almost looks like the cosine curve flipped over, but let's not think about it like that. It's not that. It is that the sine curve has shifted left or right on the coordinate plane. And we can see it more clearly if I just go through one more, let me just extend this part out just one more position, and we can see our basic sine curve right here. You see, and it's just the shift over from our fundamental sine curve has just shifted to the right, pi over 2. That's all there is to it. Now, when you construct the graph of these, involving these shifts, you're not going to do it like this. This is just for reference and just for discussion so that you'll buy into the idea of the shift. You can analyze it this way, that's fine. But just realize that when you start the process, you kind of do this. You think, well, I've got a sine curve that has an amplitude of 1 and a period of 2 pi. All right, I've got that in my mind. And now, because I'm subtracting pi over 2 before taking the sine, I know that I'm going to shift left or right in a direction I don't expect. I see minus pi over 2, so I'm shifting to the right pi over 2. So what we want to do is, when we structure the graph, we just want to start at that pi over 2 point and say, okay, here's where everything is starting, and I want to go in this direction a distance of 2 pi. So I've got 0 here, and then 2 pi plus pi over 2, you see, puts me out here at a particular point, and now I can do this, and here's where my basic curve occurs, and I can backtrack to the to the y-axis if I want to, and I can backtrack this way as far as I want to, and that way as far as I want to. But that's the whole idea, that we want to establish the the amplitude, the period, and then the phase shift. And then we're kind of operating off of the phase shift. And when you begin to write this, this interval, just make sure you have an interval that corresponds with the period. And the interval starts at pi over 2. You see the length of your shift. And then you go over the interval for your period and then make your marks, and away you go with the graph. Consider this equation. Now we see that we have the sine of a binomial, and from that form we know that we're going to have a phase shift. But to identify the phase shift, here's what has to be done. In the previous problem we had a binomial, and the second item in the binomial represented the phase shift. But remember, in that problem the coefficient of x was 1. So we have to create a situation where the coefficient of x is 1, or we have to use a different technique that I'll show you in a minute. But one way to do this, one way to identify phase shift as the second item here, is to force the factorization of whatever coefficient of x that you see, if it's not 1. So we snag 2 out of this term and we have x, and we snag 2 out of this term. Forcing that factorization, we get pi over 6. And now we see that the phase shift is pi over 6. In a direction we don't expect, we see minus pi over 6, so the shift is to the right, pi over 6. Now, let's go through all of the aspects of the graph. We know the amplitude is at the absolute value of the coefficient of sine here, and that coefficient is understood to be 1, so the amplitude is 1. The period is 2 pi over b. The b value is this 2. Now, this 2 can be identified either here as the coefficient or the outside factor of the binomial, or as the coefficient of x. In either place, it's the same. Okay, so it's 2 pi over b, 2 pi over 2, or simply pi. Now we have a phase shift of pi over 6 to the right. I mentioned that there was another way of identifying the phase shift, and I'd like to show that to you in a rather general form. It turns out that you can take this value and simply divide by the 2 here. If you take pi over 3 and divide by 2, you'll get the pi over 6, and you'll identify the phase shift. Symbolically, it looks like this, that if we have a sine bx minus c. Now, one way to do it, the way that I did it over here, is I force the factorization of the b, and that causes the situation in this fraction to be c over b. You see? So we can identify the phase shift directly as a value within our equation, or we can identify it by using the c over b idea. All right, for all of the items, its amplitude is the absolute value of the a, the period is 2 pi over b, and the b can be identified in either of these positions, and a phase shift of c over b. And c over b might be a part of the equation, or it might be identified as separate parts up here. Okay, let's get back to the graph. Now we have this phase shift and we have a period of pi, and we know that fundamentally we have a graph that, here's 1 and negative 1 for the amplitude, but we've got a graph of our basic sine curve, and we know that pattern by now, and it has a period of pi. So if we identify that period and call this pi, and therefore this would be pi over 2, and here are the other significant points, then what's happening is that the entire cycle of our curve is happening in this interval, but we want to shift the interval over to the right, pi over 6. Now, we might just say for each of these values, and let me identify them a little more carefully here, and separate them a little bit. I'm going to get messy if I'm not careful. I want to make this high and this kind of low. Okay, so I have pi. Let's put pi right out here. Then this is pi over 2. And midway from 0 to pi over 2 is pi over 4. And then between pi over 2 and pi is 3 pi over 4. All right, now these are the significant points on the graph if the graph were cycled in the interval from 0 to pi. But we want to shift it over a little bit. We want to shift it over a distance of pi over 6. Now, if I take the 0 point here and I move it to the right pi over 6, I'll get to about right here. If I take this point and move it over pi over 6, I'll get to a point right about here. And for this point, I'll move over pi over 6, and for this one, pi over 6, and for this one, pi over 6. And now I can identify the significant points on the graph by using these points, the shifted points, you see, for all of those that are related to the ones that are listed here. Now, some teachers don't mind if you do this, and if we say, okay, we know we're starting at the bottom of the amplitude here, we go to the top of the amplitude for this point, we come back to an intercept right here, and the bottom of the amplitude for that point, and then back to the intercept. So here's our graph then. Now, this might be perfectly all right for some teachers, but it may be the case that you need to identify these very important points. And I would suppose that you would want to identify them. Now, to do that, you have to add pi over 6 to 0, and pi over 6 to pi over 4, and pi over 6 to pi over 2, you see, to identify all of those special points. Now, to do that, here's what you probably want to do. Now, I'm going to just write the important points on a cycle from 0 to pi. Now, I can do it like this. I can say, okay, the important points are 0 and pi, and then there's pi over 2, which is right in the middle, and then between here and here there's pi over 4, and then between these two there's 3 pi over 4. Okay, and my phase shift is pi over 6. Now look at all of these as fractions, and think about a common denominator for all of these. You see, and identifying that common denominator allows us to perform the calculation of addition very easily. The common denominator among all of these denominators would be 12. And so I'll think of this as 0 over 12. And I'll think of pi over 4 as, well, I'm multiplying by 3 over 3. So it's 3 pi over 12. And then here, pi over 2 is, you see, in terms of 12, it's 6 pi over 12. You see, and I'm multiplying this by 3 over 3. So it's 9 pi over 12. And this is 12 pi over 12. And I think of pi over 6 as 2 pi over 12. Now, with all of that done, I'm just taking this value and adding to all of these. So 0 over 12, or 0 pi over 12, I guess is fine. 0 pi over 12 plus 2 pi over 12 is 2 pi over 12. And then 3 pi over 12 plus 2 pi over 12 is 5 pi over 12. And then 6 pi over 12 plus 2 pi over 12 is 8 pi over 12. 8 pi over 12, 8, 12, 4. You see, then we get 2 pi over 3, reducing. And then 9 pi over 12 plus 2 pi over 12 is 11 pi over 12. And then 12 pi over 12 plus 2 pi over 12 is 14 pi over 12, or 7 pi over 6. So now this is a special kind of problem that I've chosen here, but I've chosen it because of this lengthy arithmetic that we have to go through to identify these very special points. But once we have these calculations done, then the points that we've identified here, now this point, the point where we sort of started, is 2 pi over 12. And I can identify them above if I want to. 5 pi over 12. And then the next point, 2 pi over 3. And it just cleans up things a little bit by doing this kind of thing. Let's see, 11 pi over 12 is this one. And then that last point turns out to be 7 pi over 6. Okay, and that's the complete cycle. And obviously, if we need to, we can expand the graph to accommodate any interval that we'd like. Okay, so that's the idea. Let's get back to this general form. Now, we've talked about just about all of the transformations that we had talked about earlier, except for one, and it's the most basic of all. And it's the transformation where we added or subtracted some number after applying the prevailing operation. It's kind of like having all of this business and then add a value. Now, I'm using the letters A, B, and C here, so let's just tack on a D. So it's plus D. Now, D might be positive or negative, but if D is positive, then the graph will just shift up on the coordinate plane. If D is negative, it'll shift down. So we have, as an additional item in this list of items for our various identification of graphing items is a vertical shift. So we have a vertical shift that is according to D. All right, so that's the idea. Here's another one. This one involves the cosine curve. And once again, we have this idea of a phase shift along with a special amplitude and a different period as well. Well, I have elected to force the factorization of the coefficient of x, and I'm identifying that coefficient as 1/2. And I snag that 1/2 out, you see, and then I'm forcing that factorization, and this becomes pi over 2. And now I can identify, just by looking at this equation, all of the aspects of the graph that I need to. I have an amplitude at the absolute value of 2/3, which is 2/3. I have a period of 2 pi over b, and the b value is 1/2. And it's identifiable here. It would also be identifiable up here. So it's 2 pi over 1/2, or 4 pi. And I have a phase shift of pi over 2 to the right, and I know that from this. Now I could also know it by pi over 4 over 1/2, you see, but it's pi over 2. Okay, so I have all of those things. Now, with that in mind, I would just march over to the side, and I would begin my graph like this. Now, all of these graphs can look pretty much alike in that your amplitude, if your amplitude is 1, or if it's 2/3, or if it's 1/2, or if it's 50, you just put it up here on your coordinate plane somewhere and just measure the same distance down below and label it properly. I'm labeling this as 2/3 and this as negative 2/3. Now, a nice technique here is to do this, as we mentioned before. Okay, so that's the amplitude information. I have a period of 4 pi, so I might come out here and identify 4 pi, and then all of the significant positions for the basic graph of a cosine curve. Now that would mean that I would identify half of 4 pi is 2 pi, and midway between these two would be 3 pi, and midway between these two would be pi. All right, now let's go back over here. We've taken care of amplitude and period. Now what about phase shift? Well, phase shift is pi over 2 to the right. So what we want to do is add pi over 2 to all of these various points. Now adding pi over 2. Well, gee, pi over 2, this is 0, this is pi. Gee, pi over 2 is right in the middle. That's pretty easy now to add. I can identify those important points for the graph of this equation just by going midway between all of these. You see, I can do this. I can say, all right, here's an important point, there's an important point, here's an important point, and another one is over here the same distance. All right, now, if I want the values of those, and I probably do, then I want to think about all of these along with that phase shift of pi over 2 in terms of the same denominator, 2. So I want to think about this as 2 pi over 2. So 2 pi over 2, now let's just keep in mind, pi over 2 is the phase shift. So I'm thinking of this as 2 pi over 2 plus pi over 2. That's 3 pi over 2 for this point. I seem to have skipped a point. Anyway, 3 pi over 2 for that point. This one is 0 plus the pi over 2, pi over 2. Okay, 2 pi, let's see. Now, to have that common denominator situation, I'm multiplying by, I'm thinking of this as 2 pi over 1, and then 2 over 2 times this. So 4 pi over 2 plus pi over 2 is 5 pi over 2. So this is 5 pi over 2. And then from 3 pi, I want to add pi over 2. So I think of this as 6 pi over 2. Plus pi over 2 is 7 pi over 2. And this is 8 pi over 2. Plus 1 pi over 2 is 9 pi over 2. Now I have my important points. And all I need to do with the identity of these is go through the idea of the basic cosine curve. Remember, the basic cosine curve starts at the top of the amplitude. It comes down to an intercept, goes to the bottom of the amplitude, back to the intercept, and to the top of the amplitude. And now one cycle of this curve looks like this. And obviously we would extend to whatever domain is being defined for this particular function. Let's review a bit. Let's talk about the various aspects of graphing sine and cosine functions. We remember that sine and cosine functions have a period of 2 pi, and we start out by simply identifying that period. Then we end up subdividing the period into 4 parts. We divide the 2 pi distance into half, and then the halves into halves. And these positions identify x-intercepts and maximum and minimum points. Well, to identify where the maximum and minimum points lie, we identify the amplitude, and we sometimes draw dotted lines horizontally in order to identify how high and how low we'll go on the graph. And then we simply draw the curve as we understand it. Here we're drawing a sine curve. Well, we understand that we can extend the graph in either direction if our domain is beyond 0 to 2 pi. So we simply continue the pattern in either direction in order to accommodate the given domain. Let's understand, too, that all of the aspects of sine function apply to cosine function because, after all, the cosine can be regarded as the same curve except adjusted just a little bit left or right on our coordinate plane. Well, let's take a hypothetical situation here, a situation where we have an equation with variables in place of the coefficients and constants that can occur in some typical sine function. We have an A, B, C, and D value here, and we would like to examine each one. First of all, the A value identifies the amount of the amplitude. Now, the amplitude is just a vertical shifting of our graph, and the graph could shift to a position like this, for example. It's like a stretching. If the A value is larger than 1, it turns out that the stretching occurs as we're illustrating here. If the A value is between 0 and 1, it would be a compression. Now, the B value is identifying a change in our period. Now, the typical period is 0 to 2 pi. But if the B value is larger than 1, it turns out that we'll have a compression of the graph. The graph might look something like this, just be a little more curvy. And of course, we're showing that it can be extended in either direction to accommodate a given domain. All right, here's the 0 to 2 pi typical period. If the B value is less than 1, then that period could be extended like this. Let's talk about the C value. A number in this position gives rise to a phase shift, which is simply a left or right shift in the entire graph. And that phase shift is given by the fraction C over B. A number in the D position simply changes our graph vertically. It will shift the graph up if D is positive and down if D is negative. So it causes an up or down shift in our graph. Well, let's take a situation, an equation, and identify the various aspects of it and then construct the graph. First of all, the amplitude is the absolute value of A, which in this case turns out to be absolute negative 3, which is 3. So we draw horizontal lines at y equals 3 and y equals negative 3. We identify the period as 2 pi over b. In this case, b is 1/2 pi. So the period turns out to be 4. We identify the position of 4 on our coordinate plane. And now we can subdivide that area if we want to do that right now, but it might be wise to identify a phase shift first. Here, the phase shift now is c over b, which is pi over 1/2 pi, or simply 2. So our graph is going to shift 2 to the right on our coordinate plane. So we think about that shift. Now, another way to identify this phase shift is to perform a little operation in the function itself. We can force the factorization of the coefficient of x within parentheses. Here we're forcing the factorization of 1/2 pi out of that binomial. And in doing so, we can see that the second component within the parenthesis gives the exact amount of the phase shift. In this situation, we have a vertical shift also of +1. Now what that implies is that all of the aspects of the graph that we've been talking about will go up 1 on the coordinate plane. Now, of course, we can take this interval and subdivide into the points that identify sort of intercepts of this little interval, and maximum and minimum points. Now, of course, we can just draw the typical sine curve as we understand it. So here comes a sine curve going to the top of the amplitude, bottom of the amplitude, and so forth. But let's not forget that there's one aspect of our function that we did not consider, and that is this leading negative sign. And that negative sign will cause the graph to actually flip over on the coordinate plane. So we notice this minus sign here, and the graph has to flip over. Now, it's a reflection, in this case, in this interval that we've identified. In times past, we've noticed that that reflection was in the x-axis. It's actually in the axis of symmetry involved in the function at hand. So we flip over at the position at hand here. And now, of course, we can just extend the graph to the ends of our domain, whatever it may be, and our problem is done.